we are on chapter something 12. Oh, that sounds good. Chapter 12. We're on chapter 1. Welcome. Hope you enjoy the semester. All right. All right. So chapter 12. I think last time we got into our friends aldehydes and ketones. Remember again, functional group wise, we're talking carbon oxygen double bond, which is referred to as the carbonyl group. And an H is the functional group there of our aldehyde. For our ketone, it is again a 3-carbon run where we have the carbonyl carbon there in the middle with a double bond. In terms of naming these guys, we do end here with Al. We do not need to, as we talked about, give the location of a carbon-oxygen double bond, as it has to always be pretty much at the end of the molecule because of that hydrogen that's there. Although we do not need to give the location of the carbon-oxygen double bond, that is always, in terms of numbering, the priority, and that is always carbon number 1. So if there again happens to be other groups attached, like we saw, we would number accordingly, and again put our groups in alphabetical order based on their location as well. For our ketones, we do end in ONE, basically. And same idea, kind of like the aldehyde, the ketone carbonyl carbon, which is this guy here, will never be at the end because you do need 3 carbons in a row to make that functional group, with the middle carbon there in that 3-carbon run having the double bonded oxygen. So as close as you could get to the end would be like the 2nd carbon in is really as close as you could get with that carbon oxygen double bond. We do not necessarily need to use a number where the carbon oxygen double bond is unless we get to like 5-ish or more. When you start getting some options as to where they could be, or multiple options of where it could be, then we do need to use a number just like anything else, like an OH or a double bond, triple bond. We want to give the carbon oxygen double bond the smallest number. That's the priority in terms of numbering. Once you lock that into place, then obviously you name all your groups and number all your groups accordingly, whichever way gives it the smallest number. Again, if it is a tie or something of that nature, then you would want to default to groups as alphabetical, probably your next sort of important thing. We talked about how we form these guys, and we do form these guys primary alcohol, right? Doing a little oxidation action gives us our aldehyde. And that is really the loss of H2 that's happening there. And we can also, as we talked about, oxidize our aldehyde one more step. And we're basically kind of going from this situation where we get rid of these hydrogens to our double bonded aldehyde to a carboxylic acid. The carboxylic acid oxidation is really we're gaining some oxygen, and the oxygen gets inserted right there, and that makes the carboxylic acid functional group, which looks like this guy here. So we can go all the way through there and go through oxidation reactions. By the way, we could also start at the right-hand side here and go the opposite direction, and those would be all reduction reactions. Where we could reduce down the carboxylic acid to the aldehyde, and then reduce down the aldehyde to the primary alcohol. So going in the opposite direction is the reduction part of the reaction. That leaves us our secondary alcohol, which again, in that situation, you got something like this you're starting with. Obviously not the entire molecule, but just kind of draw something like that. We're going to knock off those 2 hydrogens through the oxidation, and that's going to get us to our ketone, which we will make our double bonded there carbon, and there'll be another carbon perhaps on this side as well. That'd be good. And again, in terms of oxidation, we're not going to get anything sort of happening at that point. We could also obviously reduce it back. And again, that would be our reduction reaction, which is adding our hydrogens basically back in through there. We talked about a test at the end there, a Benedict's test, which can be used to look at really this sort of oxidation move here. And again, the formation of that carboxylic acid, as it gets oxidized, the aldehyde will reduce the copper that's in there, and it will go from copper to, which is kind of like a bluish color, to a copper 1 sort of complex there. This something you probably saw on Monday, which is kind of an orangey reddish type of color that would develop. We won't get that coming down here. Thank you very much. As again, we won't have that oxidation happening. Again, really because missing that hydrogen is sort of important, as we talked about, I think, last time as well. Any questions on some of that stuff there we talked about? So in addition to the Benedict's test, another test is sometimes used for really the identification sort of aldehydes to carboxylic acids. Is what's referred to as the Tollens test. And the Tollens test, same sort of principle as the Benedict's test, except that they use silver, and sometimes referred to as the mirror test, because in this case, as our ethanol here gets oxidized, our silver with a +1 charge gets reduced. And that means that it goes from silver with a +1 charge to silver with no charge. And again, as you can see in that picture, kind of gets very silvery and like a mirror type of color. So if you were to do something like the Tollens test, that would also be an equivalent sort of test as what you did there with the Benedict's test for a positive oxidation, again, of an aldehyde to a carboxylic acid. Again, there's our carboxylic acid right there. And once again, nothing big changes as you oxidize your aldehyde to a carboxylic acid. All you're going to do basically is keep everything the same. Just insert the oxygen there in front of the hydrogen to make this group there at the end. And then obviously we talked about our Benedict's test there with our copper 2 going to copper 1 in that particular case there. Now, we sort of touched upon this, which are the reductions that occur, and reduction reactions for both aldehydes and ketones, I would say, is pretty much equivalent to what we talked about when we did like a hydrogenation reaction with a double bond. So if you had a double bond and we added hydrogen to it, as we talked about, really the only thing that's going to change here is we're going to make that into, again, a single bond to allow room for those hydrogens to come in. And that will then allow room for those hydrogens basically to be put back on. Now, when we talk about really the aldehyde or ketone, it's pretty much the same deal that's happening here, except that it's not really the two carbons that are double bonded. Obviously, with our aldehyde or ketone, we got this, right? And we'll just do a nice simple one there. Looks like that. So we have that where we have our carbon oxygen double bond. And if we did our ketone, we have our ketone that looks like that. So if we were going to add hydrogen to this guy, which is basically the reduction reaction that's happening, once again, it's all going to proceed at that carbon oxygen double bond in this case. So it's really all about that spot right there. At the point right now, we really don't have any room to put the two hydrogens. A reminder as well, not really drawn all the time, but there are two pairs of non-bonding electrons there, which is why it's full at this point with those non-bonding electrons. So what's going to really happen here again is pretty much the same thing that happened up here. We really just need to make room for it. So we're going to get rid of the double bond, and absolutely positively nothing else changes. So we'll just have our CH3. We're just going to turn that into a single bond, and we will still have our H. By doing so, what that does is pretty much opens up a spot at the carbon and the oxygen there for each of them to gain a hydrogen. And when we do that, we would just put a hydrogen on one there, and we could slap a hydrogen on there. And as you hopefully know, that now returns us to our primary alcohol in this case. So this is obviously our aldehyde. So the reduction reaction pretty much of an aldehyde or a ketone, as we kind of looked at there a second ago, is really the opposite reaction of the oxidation step. We're just going to put the hydrogens back on, and just like they come off, they go back on, one to each element within where the double bond's located. It doesn't matter, you know, how many more carbons or whatever else is there. It's going to always happen right there. So if we did it, for example, to this guy down here as well, all you really should focus on is right there, and that's all you need to do is just turn it into a single bond. So we would have this, this, and this. And you can see I pretty much drew that in like 1 second because I'm just copying what's there. By making that a single bond, again, we're now giving ourselves the room that we need to put our hydrogens on. And now that returns us to our secondary alcohol. So the reduction reaction, I think it's pretty much the same deal that's going on there with your carbon-carbon double bond. It's a good way to think about it. And once again, we don't want to do anything fancy or crazy when we do these things. As we talked about many times, pretty much what you start with is kind of what you end with. Just a small little bit of it changes. So don't get too creative with it. Just copy in the sense what you started with and you should end with. Question on that one there. So that's what we see here. Once again, nothing happening except for the double bond that takes us over here and makes our alcohol back, and then our other alcohol there same way. So why don't you let's do this one. Let's just draw one here. Let's say we had so let's oxidize this guy, and let's do and let's oxidize this guy. So draw the products that you would get from these two guys here. Did I say oxidized? No, I didn't mean oxidized. Huh? That's the wrong one. Not oxidized. Let's reduce these guys, maybe. That would be much better. All right, so plus some H2. That would be good. There we go. Which, again, are reductions here. That's what I think I want. There we go. Okay, so let's take a look. Once again, in this case, it's all about here. We're adding basically 2 hydrogens. So as we talked about, we basically just need to make room for it. So I'm just going to come down here. I'm just going to copy exactly the way it looks. And when I get to my carbon oxygen double bond, I'm going to turn it into a single bond. And again, that is what's going to allow me now some room. And we're going to pop a hydrogen there and a hydrogen there. And now we should be good. Yeah. Any questions on that one there? Same thing down here. This is where all the oxygen is going to happen. And I'll go down this way maybe. So we'll go, maybe I'll go above. So we'll go CH3, CH2. We're going to turn that into a single bond, a C and an H. I forgot earlier there. Was that on there? And we'll come down this way, CH2, CH3. Now, in this case, we're going to put a hydrogen there and a hydrogen there. And that we should be good in that case, yeah. Any questions on that there? So reduction, opposite of oxidation, double bond, single bond, add some hydrogens. Don't get fancy. All right. All right, so I want to try this one. Select the product for the oxidation of the following. So take a moment. Think which one should be the right one here. It doesn't matter. Sometimes people will write it like if you're talking about this part. Sometimes people will write, yeah, they'll write like that. Just indicates that the carbon is attaching to the carbon. So, or sometimes people will just write CH3. No difference as long as you have the right number of carbons and hydrogens, it'll be okay. All right, so here we are starting. That looks alcoholish, right? That is an alcohol. And that is what type of alcohol? It is a secondary alcohol, which, by the way, if we know when we oxidize secondary alcohol, it is a ketone, which means I don't really care about drawing it because I can pick the only ketone that's here, which is B, right? So that's why it's good sometimes just to know what it makes, right? Besides the drawing part of it, because, you know, if it has something like that. By the way, what's happening here, right, is we're going to take out that hydrogen. We're going to take out that hydrogen and we're going to double bond it up right there, right? And that's what's going to get us to our ketone. Question on that one there. All right, so pick the two products here, I think. Maybe. Select the product when this undergoes each of them. I feel like the letters in the wrong spots. I feel like the C should be here and the B should be there. All right, so think about what you get on the first oxidation and then what you get on the second oxidation here. Okay, so let's take a look. So first off, this is a alcohol as well. So that's a primary alcohol, which we know when we oxidize it should hit us a aldehyde, which means we already know that should be the right first answer. But we'll see how we get there. We're going to take out a hydrogen there, right? And take out a hydrogen there. And that is going to leave us CH3, CH2, CH double bond O, right? Plus some hydrogen now, which would be this one. So that should be the first guy that you get. Then if I oxidize the aldehyde, I will get a, I'll just do the arrow this way. We'll get a carboxylic acid. And that means that all I'm doing is then in this oxidation, basically put in an oxygen there. It's gaining oxygen. And that will get me that guy. Yeah, that's the second one. Any questions on that one there? So again, sometimes it's good just to know, like I said, kind of what you get, what you're starting with. You do this to it, you get this. Can be helpful sometimes. Any questions on those there? All right. Good on that. All right, the last thing we're going to talk about in this chapter is a couple of reactions that aldehydes and ketones will undergo actually with alcohols. So if you have an aldehyde or a ketone and they react with an alcohol, there's a couple of things that sort of occur, and we're going to talk about what those are right now. So we will start with a aldehyde here. We just start with this aldehyde. Why not? So if we take an aldehyde, such as this guy here, and we add one alcohol to it. I'm just going to draw the alcohol like this. We'll just do methanol here. A little methanol, which is obviously an alcohol. We will get a reaction that's going to happen. And as you could probably imagine, if you had to venture a guess as to where the reaction is going to take place on the aldehyde, where do you think it's going to happen? Yeah, it's all going to happen right here. So that's where it's going to happen. Now, remember that this carbonyl group is really a polar group. So like the top part here is more negative, right? And the bottom part's more positive in this case, right? So how this alcohol actually adds in is it actually adds in as two things. It adds in as a hydrogen, which is kind of like a H plus, if you will. And it adds in with the second part here, which is this like oxygen carbon group, which is really this guy here. Yeah, that's really that guy. And this is actually a negative charge. Is as a negative charge on that guy, basically. Yeah. So what happens is obviously just like before, we really don't have any room there to add anything at this point. So we're going to do our normal thing here, which is we're going to take the double bond and just make it into a single bond. So the first thing that we would do is pretty much have the exact same thing. We're going to make a little bit of room here. And we want to make room for those two things that are basically going to come in. The one thing that we do know is opposites attract, right? So my positive hydrogen here is going to be attracted to the negatively charged oxygen in that case. And this negatively charged guy here is actually going to be attracted to the carbon part of that bond. So that is where those guys will end up. The hydrogen will end up on top. And this oxygen carbon group will actually end up there on the bottom. Now, this has a special name when you have this sort of arrangement. This is what is known sometimes as a hemiacetal. So what are the major components of a hemiacetal? It is on that carbon, this carbon right here, where that double bonded oxygen was, you will find a OH group. So you kind of think of, that's kind of what the hemi part of that name kind of means. You will find a oxygen carbon group, which is what that guy is right there. And you will find a hydrogen. And it's called an acetal because it comes from a aldehyde. So that's where the kind of that part of it comes from. So those are the essential kind of three things that you find on what is referred to as a hemiacetal, that carbon where basically the carbonyl group was, and that double bond, you'll find definitely an OH group. You'll find a hydrogen, and you'll find some type of oxygen containing group, oxygen carbon containing group that basically came from an alcohol. Now, if you took that guy and added not one alcohol, but then decided to add another alcohol, your hemiacetal that we just made there will be able to sort of take on another alcohol. So it could actually be the same alcohol or a different alcohol. We'll use the same one here. So we're going to add our same alcohol. And in this case, it's going to add really the same way. We're going to have like our H plus, and we're going to have this oxygen carbon group here, which is technically negative as well. So what's actually going to happen in this particular case is the hydrogen will actually come on over here to the OH, and it will actually make water. And that's going to pop off that OH basically as water. So those two guys are going to come together and make water. And then what happens actually in this case is that water comes off, and everything else here stays exactly the same. So you could just like copy exactly the same. Everything stays exactly the same. But there is one problem with what I just drew, which is the carbon, right, is missing something, right? It always got 3 bonds. So that is actually where this guy is going to end up. He's going to come into that spot because when that water comes off, that carbon becomes more positive and it allows that negative guy to be attracted to it. And it will actually add right there where the water basically came off of. And we will get this guy here, which also has a special name. This is what is known as an acetal. And the difference between a hemiacetal and an acetal is when you look at this carbon, there is no OH. Yeah. So again, you can think of the hemi like there should be an OH, that's that part of it. There's no OH. There's actually two oxygen carbon groups. That group there and that group there. And there's also a hydrogen, which is right there. So if you take an aldehyde and you add just one alcohol to it, it will make what is referred to as a hemiacetal, which basically means you'll break the double bond, you'll make an OH group always, and whatever other part of the alcohol that's there, that's past the oxygen and the alcohol and carbon, those will go to the other side of the carbon. If you add two alcohols, you will get two oxygen carbon groups that basically will attach. Any questions on that there? So why don't you try one? Let's say we had and let's add want to add two of these guys here, I think. So what do you get after the first one's added? And what do you get after the second one's added? All right, draw up what you will get here. Okay, let's take a look. So once again, we're adding two alcohols here. It happens to be the same. They're going to come on basically one at a time since we're looking for what we get at each step here. In this case, you can kind of think of it, if you want to kind of turn it around, you can, and kind of draw it out like this. So the first thing that's going to happen is one of these alcohols are going to add on. And again, in this situation, this is basically how it's going to add as those two things. Once again, here, we need to make some room for that to happen. So all it's going to change is that's going to become a single bond. So the first thing here, we would have something like this. And we're just going to drop a single bond in there. That again is going to make room for these guys to attach. Remember that this guy is really like H plus, which is positive, which will be attracted to the negative there of the oxygen. The remaining part here is that oxygen carbon group that's going to find itself over here at the carbon. Any questions on that one there? That again is what is referred to as a hemiacetal. And again, the major parts of the hemiacetal is OH group, hydrogen, oxygen carbon group. So those three things on that carbon that was in the double bond. Any questions on that? Yeah. So where does the 2 come in? The 2 comes in because now we're going to add the second alcohol to this guy. Yeah. So they do sort of add one at a time. So if you had this problem, really the thing that you should draw at the end is what we're going to draw right now. But since we talked about both parts of it, I just kind of did both steps. But because we are adding 2 alcohols, at this point, what's going to happen is that second alcohol that's there is going to come into play. And now what's going to happen is we really need to make room for this oxygen carbon group that needs to come in. And the way we're going to do that is, if you remember, our OH and our H are going to come together to basically make water. So that's going to make water. And essentially when that does, that is going to leave that spot on that carbon empty. And that empty spot's where the other oxygen carbon part could come in. So the rest of it, though, is the same. So we're just going to draw everything the same. And all I did, frankly, is just copy everything that was right here. So I just copied everything that was right there after I got rid of the OH. And now we can see, right, we have that empty spot for the oxygen carbon group, and that is where it's going to land itself. And it will land itself right there. And by the way, it's not that fancy either. It is exactly what it says there. That's an oxygen, CH2, CH3. It basically just lands right there. And that will get us to our acetal. So to answer your question, if this was like a question where you had that and had the two alcohols, really the thing that you should draw is this right here, this end product guy that we just drew down here. That's really what you get at the end of that, is that two oxygen carbon groups. And again, the main parts of a acetal, you have two oxygen carbon groups and a hydrogen group. And that's different than the hemi because the hemi has the OH group in there, right? So that's sort of the middle step all the way across. So one alcohol drops you right here. Both alcohols takes you all the way across. Any questions on that there? Now, we could also do this with ketones, and it's pretty much the same deal. It works exactly the same way, except there's a few things missing because we're starting with a ketone rather than an aldehyde. So if we just take a nice simple ketone, and we'll take a nice simple alcohol here. First part of this is pretty identical. We are going to have, again, all of our action here, right here at the carbon-oxygen double bond. And just like before, it's going to become a single bond. So that's all you have to do is draw that up as a single bond. This alcohol will once again add exactly the way the other alcohol did, which means the hydrogen should end up where? Yeah, it should end up at the oxygen. And the oxygen carbon group should end up on the carbon. So that's a good way to remember it, which is you put the part of the alcohol that has carbon on the carbon, right? So that's where that ends up basically. That makes here a hemi. Some books will still call it an acetal, but some books will call it a hemiketal because it comes from a ketone, yeah, brushes an aldehyde. It has the same characteristics as a hemiacetal, except there's a slight difference. And that slight difference is it still has an OH group. It still has an oxygen carbon group, but it does not have a hydrogen. It doesn't have a hydrogen on it because it started as a ketone. So this guy will have an OH group, will have an oxygen carbon group, but it will have no hydrogen on this carbon here. And again, that's just because it started as a ketone rather than an aldehyde that had the hydrogen in that spot. Question on that there. Now, as you could probably imagine, just like our other guy, we could add a second alcohol to this guy and we will get something that will occur. So if we take our hemiketal here and we add one more alcohol to it, we'll add the same alcohol, why not? Pretty much the exact same thing happens. We're going to make water. And again, we're going to take the H from there and the OH from there, and that is what's going to make water. And once we make that water, just like we did on the previous one, nothing else in the hemiketal changes. So this part of it, exactly the same. So you can just copy it exactly the way it is. So it just stays the same. But what that also does, right, is it opens up that carbon for the other part of this alcohol, the second alcohol. And that is what's going to end up here, OCH2, CH3 in this case. This is what is referred to as a ketal. And it's like an acetal, except that it comes from a ketone, basically. And it's very similar to a acetal, but it has 2 oxygen carbon groups and no hydrogen still. So 2 oxygen carbon groups, no hydrogen. Any questions on that? So this is what happens when you take an aldehyde or a ketone and you react an alcohol with it. If you react with either an aldehyde or a ketone and you react it with one alcohol, you'll get to like the middle step. You'll make that hemiacetal or hemiketal. That's the guy that should have the OH group on it. If you react an aldehyde or a ketone with 2 alcohols, it will take you all the way to the end where you won't have any OH groups, but you will basically put 2 oxygen carbon groups that come from the alcohols onto that carbon, and you'll end up there. Any questions on that there? All right, that wraps up, I think, this chapter. Yeah. I feel like I have no more slides. It's just blank. Okay, we are continuing on here to, like I said, chapter 14, which is all the rest organicness. And then we will go back to 13, and then we'll just go after that. Maybe, I don't know. We'll see. This is not on the exam, yeah? So what we just finished out of chapter 12 is the last chapter that will be on our 3rd exam coming up. So I guess this is like finals type information, yes. Not to scare anybody, but is it 3 weeks to the final from today? Yeah, 3 weeks from today, final action happening. Good times had by all. All right. So chapter 14 here is all the rest of the organic groups we didn't get to yet. So we're going to talk about carboxylic acids. We'll talk about esters, amines, and amides there. We'll start with our carboxylic acid, which we just kind of saw not too long ago. Carboxylic acid functional group is the carbon-oxygen double bond and an OH happening there. Very often in formulas, they oftentimes will run those guys together as like COOH. So if you see that like in a molecular formula, that's usually meaning this carboxylic acid group. It actually has 2 polar parts. It's got our carbon oxygen part here, and it's got our oxygen hydrogen part here. So a lot going on here. We saw how we make a carboxylic acid not too long ago. That is coming all the way back from a primary alcohol, which was, I guess, oxidized into an aldehyde, which gets one more time oxidized into our carboxylic acid. So remember, this is what we get when we take our aldehyde and we oxidize it. This is where we're inserting the oxygen, if you will, inserting that oxygen right there into here to make this functional group. Now, because it does consist of both of these groups, it does give the carboxylic acid some very special properties, including the idea that it can hydrogen bond very, very well in multiple locations, which makes it very, very soluble, for example, in water. It also can, for example, hydrogen bond with itself in multiple places as well. If I could draw it, let's draw 2 of these like this. Like that. So for example, we can have our hydrogen bonding here happening here. We could also get some hydrogen bonding happening at the carbonyl as well. And it creates this sort of dimer that could happen where they bond to each other really, really tight. So as I might have mentioned it before, carboxylic acids is really the one and only thing are one of the few things that when we talk about boiling points and melting points and sort of the high end of that actually will beat an alcohol. So because of that ability to really hydrogen bond in a couple of locations with itself, it will make a lot of these sort of dimers together. It actually will have a much higher boiling point than an alcohol, which obviously was our champion up until that point, right? And we had our aldehydes, our ketones, and at the other end of the spectrum, right, we had sort of our alkanes alkenes and alkynes, which are using dispersion forces at very low boiling points and melting points. So boiling point increasing, melting point increasing as you head typically in that direction, because again of that ability to hydrogen bond really well. When we name carboxylic acids, you could replace the E on the alkane name with oic acid. So here we are still looking for the longest carbon chain. It has to contain this group. And because this group, much like the aldehyde, has that hydrogen at the end, means that this group should always be at the end as well. So you can never have this group in the middle because that hydrogen will have too many bonds. So much like the aldehyde, that group should always be at one end of the molecule or the other. It'll never be anywhere else. With that being said, that also means that we really do not have to give the location of where the carbon-oxygen double bond is located because it's got to be at one end or the other. But just like what we do with aldehydes, this carbon is considered carbon number 1 in terms of numbering. So wherever that is located, that should be your carbon number 1. And then obviously if there are other groups attached, everybody else would be named accordingly. So here we have 1 carbon based off of methane, drop the E, this becomes methanoic acid. This has 2 carbons, which is based off of ethane, and that will then become ethanoic acid, which is, by the way, also known as acetic acid, which is also known as the major component of vinegar, right? So that is basically acetic acid in that particular case. So again, we have some of these other names that are sometimes used for these guys. Now, if we do have groups attached, like I mentioned before, we do want to give the priority to this carbon. And as you can see, it is at the end. So we would still look for the longest carbon chain. So 1, 2, 3, you could go up to get 4, or you could go straight across to get 4 as well. No matter which way you go, 4 looks like a winner. That is where the butane becomes butanoic acid part comes into play. Because this has to be carbon number 1, that would be carbon 2, that would be carbon 3, and that is where we would find our methyl group. So this would be 3-methyl butanoic acid. That is a benzene ring next door with a carboxylic acid off of the ring. We might have talked a little bit about it the other day. But that's going to be known as benzoic acid. Yeah. So this is benzoic acid based off of benzene and putting an oic acid at the end. Now, when we have groups that are attached, the carbon here that has basically this functional group on it will be considered carbon number 1. So carbon number 1 is not, in this case, when you have a benzene ring attached, is not the carbon that's off the ring. It is the carbon that that group is attached to, will be carbon number 1. And because this is a benzene ring, it's got the 3 double bonds. It doesn't matter which way you number. You want to go whichever way is the smallest. So it looks like clockwise will do that for us, giving us a 2 and a 3. And there's dichloral because there's 2 of them. So that would be 2,3 dichloral benzoic acid. So a little bit different. It kind of has the group hanging off of the ring, but it's still considered all kind of one thing, as that's the functional group of it. And again, here when we're numbering, we still want to number off of the benzene ring, for example, here, and give the locations of where those guys are located. Any questions on that there? So here are some common names for these acids. We have methanoic acid, which is formic acid. That is a name that's still used a lot. Ethanoic acid and acetic acid. I would venture to say most people will call it acetic acid versus ethanoic acid, but the formal name is ethanoic acid. But acetic acid is a very, very commonly used name still today. But for us, if you were given this and asked to name it, IUPAC name, ethanoic acid is probably the way to go. But you should know, again, that those 2 things are kind of the same thing. Propanoic acid and propionic acid and butanoic acid So for us, we will kind of stick with the IUPAC way of naming these guys. And I would say out of this list, maybe the first two here in terms of the common name, those are again ones that still very commonly sort of pop up. So you should have some frame of reference that, formic acid is methanoic acid and acetic acid is ethanoic acid. Any questions on that there? There is our line structure way of doing our carboxylic acid, which means you do need to write the OH there. And obviously this would be where our carbon would be, right, in that case. As I mentioned, formic acid does come from, for example, red ant stings. That doesn't sound good. Vinegar, sour taste is due to that ethanoic acid or acetic acid in there. All right, so write the IUPAC name for this guy. What we would call this guy here. Take a moment or two and see what you come up with. All right, let's take a look. So obviously here we want the longest carbon chain that has our functional group. We should see the carboxylic acid functional group there. So it looks like 1, 2, 3, 4, 5 looks like a winner. Your only other option would be starting here and going 1, 2, and 3, which is obviously less if you kind of go down. So 5 carbons is based off of pentane because this is a carboxylic acid, which we see right here. This is then going to be pentanoic acid. Remember again here, we do not need to give the location of the carbon-oxygen double bond, but that is carbon number 1, which means that carbon number 2, I have my lonely line, which is a methyl group, right? And that would then be a little 2-methyl pentanoic acid. Yeah. Any questions on that one there? All right, so why don't you give the names of these guys, and then why don't you also draw, let's do, let's do 4-chloral, 3-methyl hexanoic acid. Why don't you draw that? And why don't you draw let's draw 4-ethyl draw 4-ethyl oxanoic acid. Okay, let's take a look at the first one here. You can actually get 3 both ways. You go straight across here and our carboxylic acid group there, or you obviously could go across and then up. We'll also give you 3. 3 does look like a winner, and 3 is based off of propane, which means this then is going to become propanoic, if I could get that right, propanoic acid. This would be carbon 1, 2, and 3, and there's our methyl group at carbon number 2. So this is going to be a 2-methyl propanoic acid in this case. Any questions on that one there? Next, we have the benzene ring, which once again, this entire thing, along with our carboxylic acid, it's all going to be kind of the base of the name. So that is a benzene ring with a carboxylic acid. So the base of that is going to be our benzoic acid. And remember that here we do want to come to the ring and start numbering 1 where this carbon is attached. And that would be 2 and 3. So a little 3-bromo benzoic acid. Yeah. Any question on that one there? All right, so we're going to draw. So we're going to draw just like normal. So hexanoic acid tells me that it is a carboxylic acid, and the hexane part tells me it is 6 carbons. I'll go down here, maybe. So 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. Now we know that the carboxylic acid group does need to be at the end. So since you're drawing it, you can put it on the left-hand side or the right-hand side. I'm going to go right-hand side. Why not? We'll mix it up a little bit. We'll put it over here. And because I put it over there and forgot my oxygen, now it's better. Now that I put my oxygen in there and put it over there on the right, that is going to be carbon number 1, right? Which means now if I travel down this way, 2 and 3, I have a methyl group. So that's going to be a methyl group. And that takes care of that, takes care of that. And then at number 4, which should be right here, I have a chlorine. Just like normal, everything else here is just going to be hydrogens. So you get carbon to 4. So we need a couple there, 1 there, 1 there, a couple there, and a 3-pack there. Yeah. Any questions on that one there? All right, coming up to top, I got that's 8. They say. 4, 5, 6, 7, and 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm again gonna put my functional group over here on the right. You could put it on the left if you like. That's going to be carbon 1, which means for me, carbon 4 would be right about there. And now we're just going to fill in our hydrogens. Obviously, these would be the condensed structures. If you were going to do a little line structure, kind of the same idea. We'll start with 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. We'd bring that down with an OH and that. That would be carbon 1. And 2, 3 would be a methyl. 4 would be a chloral. And it would have something like that. Yeah. Any questions on that there? All right. Was Okay, let's take a look. Once again, hexanoic acid, similar to one we just did. We'll do the line structure here. So 1, 2, 3, 4, 5, and 6. We'll bring it down and put our OH and our double bond happening. That's going to be carbon number 1 for me, which means 2, 3, 4 is right about there. And we'll have something that looks like that. Any questions on that one there? All right, so let's talk a little bit more about these properties of carboxylic acids. Carboxylic acids basically will do sort of acid-base chemistry, and they will create what are sometimes referred to as carboxylate salts as they go through an acid-base reaction. They're used for preservatives, flavor enhancers, and seasonings. And as I mentioned before, they are really polar because they do have two very polar groups. They have, again, that carbon-oxygen double bond, which is polar. They have that OH bond, which is also very polar. So they're able to pretty much bond very strongly to each other. That also allows them, as we will see here, to be fairly soluble in water because it's going to be able to hydrogen bond with water very easily because of that. So carboxylic acids form hydrogen bonds with water molecules, and they're able to do that at both locations. So what I mean by that is, if we just look at the carboxylic acid group, we could have our water, and it's able to hydrogen bond right there. But also here, as we see with our carbon-oxygen double bond, which is negative, if we have our water, it could also hydrogen bond there. So it gives it a lot of places where it could interact well with water, which makes it very soluble in water. But it is still like any other organic molecule, which means if you build out a bunch of carbons and hydrogens and it gets really big, solubility is really going to start to drop as well. So as you can see there, with 1 to 5 carbons, you're going to have these carboxylic acids being very, very soluble in water, as it's not going to have too much trouble hydrogen bonding with water. As we do increase above 5 or more carbons, again, we're going to see a drop off in that solubility, which is what we see there. Right around hexanoic acid is slightly soluble, which again usually means more so on the non-insoluble side than it being soluble. We also talked about the idea that, again, it is very strong in terms of boiling point and melting point because of its ability to really hydrogen bond with itself. So again, you know, I draw it a little better than I did last time, you know, something like this. And it's able to kind of hydrogen bond with itself and make a dimer. I should have flipped it the other way, but it will basically bond with itself in 2 places as well through hydrogen bonding, which again is why it's able to have a pretty high boiling point and melting point, because that's going to hold it together with itself really, really strong. And it's going to take a lot more energy to try to break those guys apart. And that's going to translate to higher melting points and boiling points. So as I mentioned before, because it can kind of do that and make what's sometimes referred to as a dimer, which is 2 parts of it binding to itself, is one of the few things that can kind of beat, again, alcohols in terms of boiling points and melting points. Now, as I mentioned, it is really an acid, so it could do pretty much our Bronsted-Lowry definition of acid and bases, which you remember from chapter 10, I hope. That is a proton donation and exception. So this is our acid, which means it's going to donate the H plus over to water, which is acting as the base in this case. And when it does so, it will make this guy right here, which is a carboxylate ion. And sometimes there may be something like a sodium or something in there, and it will make hydronium ion, and that is going to make it acidic in this particular case. So it will pretty much do your acid-base reactions like we talked about when we did the acid-base chapter. That's acetic acid, by the way, and it will basically dissociate into acetate and H plus. But it is typically weak acids, and again, it will mainly stay together as it's going in both directions. So write the chemical equation for dissociation of butanoic acid in water. And basically, we would start with butanoic acid, which is how many carbons? Is 4. With our carboxylic acid group there and filling in our hydrogens. We're going to go with water here. Once again, this is going to be our acid. This is going to be our base. We're going to get the hydrogen to donate over. That is going to make H3O plus. And it will make this guy exactly the same, except you rip the hydrogen off and it'll become negative charged. So everything else will stay the same. and it will become negatively charged in this case, right? This is the acid, and just like in acid-base chemistry, conjugate base, yes. A little conjugate base action happening. That is your base, and this would be your conjugate acid, yeah, just like we talked about in that Bronsted-Lowry sort of definition, yeah. So it works the same way, maybe basically just transferring an H plus over, yeah. And just like we talked about when we did that, when somebody loses an H plus, they become one more negative, which is again why the acetate there has a negative charge on the right-hand side. Any questions on that there? There it is, neater, I suppose. All right. Now, it also, because it's an acid, in addition to, you could do the Bronsted-Lowry definition, it could also do just a regular old acid base reaction. So we could take our acid here, like methanoic acid, and our sodium hydroxide, which is a base. And if you remember, when you take an acid and a base together, you make a salt and water, right? And it works the same way, just like it did when we talked about it in chapter 10. The H from the acid, which will always come from the OH part of it in this case. And it is the OH here from the base. That is what makes our water, right? H and OH will give us our water. And then pretty much everything else will remain the same on our carboxylic acid. This part of it is exactly the same, except it now has a negative charge. What makes it a salt is it's an ionic compound, so it has the sodium ion with it as well. So that is what makes it the salt part of it, is that positive, negative ionic sort of situation that's happening. So if you react a carboxylic acid with a strong base, you basically will make a carboxylic acid salt, is referred to, and you'll make water, just like a kind of normal acid-base sort of reaction. In terms of the carboxylic acid, as we see there, nothing really changes other than you just take the hydrogen off. So everything else will basically remain the same as you go through there. It will become more negative as well. Question on that there. Here, the carboxylate ion is named by, who cares? We're not going to name it, so we're not going to name it, so don't worry about it. But here, if we take a look at the reaction again, we have our carboxylic acid, which is H, and OH, which is going to give me my water. And once again, everything else on the carboxylic acid remains exactly the same, except obviously it gains a negative charge. And once again, we have the potassium there as the salts. Yeah. So strong base in carboxylic acid, salt and water. Carboxylic acid just kind of dissolving in water and dissociating will lose its H plus, kind of like a normal weak acid basically will do. So
doing this equation, do we have to put the charges on the salt?
Yeah, so typically you would to imply that it is a salt. So for example, why don't you do this one? Let's say we had this guy here. So go ahead and draw what you would get here. And then for this one, why don't you draw what you... Okay, so let's take a look. So the first one is really our acid and water. So it's just going to dissociate. So in this case, water is going to act as a base. So this is the one where we're just going to get our hydrogen to basically pop off over there to water. And that's going to make our H3O plus. And we will then get pretty much what's left here. Exactly the way it is. So nothing's going to change. Except obviously we lost the hydrogen. So what that means is now will become one more negative in this case. So, and again, that's basically our acid, just break it apart in water, basically it's dissociating. Really, it's going in both directions in this case. Any questions on that there? Second one, though, we are getting a reaction between an acid in this case and a strong base. And this is going to be kind of like a regular acid-base reaction. And one thing that we will make is water when we do that and a salt. So once again, when we have a strong base and an acid come together, that is where we're going to generate our water from, the H from the acid, the OH from the strong base. And that is going to get me my water here. Maybe it'll get me my water. And then at that point, the acid part pretty much stays the same. And we'll draw it exactly the same here. And it will gain a negative charge. Now, if you're just keeping track of everything, the only thing that's left over is the sodium. And that is technically floating around and would be attracted to the negative part of that guy. So to answer your question, you do need to kind of include the charges there to indicate that they're not sharing electrons or something like that. That's sort of an ionic type of situation happening there at the end. No, it will be attracted to it, and there's no sharing of electrons, but the attraction would be between these two. Truthfully, it's a salt, which means in solution. They're really not together. The sodium's just floating around, and this entire giant negative guy is floating around separate from each other. So remember, a salt's pretty much a strong electrolyte, so it'll break apart. So in solution, they're not really together. They're kind of floating around, but in an equation, we kind of put them together just to balance out the charge. Yeah. It does remain a double bond. If you're talking about the one on top, yeah, it does. So absolutely nothing changes in the molecule with a carboxylic acid in these two reactions. Nothing changes other than in the first one, we're just going to donate the hydrogen to water to allow it to break apart. In the second one, we're going to get rid of the hydrogen to make water with a strong base. But everything else stays exactly the same. Nothing else breaks in this one. Yeah. Other questions? So this is not like the only time usually we will break something that's like a double bond is if we do some type of addition reaction, like you're adding two hydrogens, we're adding like an H and an OH to the double bond. But in this case, we're just sort of reacting these guys together. So we won't get that addition sort of reaction occurs. Other questions? It doesn't, as long as it's on the right-hand side of the arrow. Yeah. And it really doesn't matter. I drew that one that way. I could have turned it around and drew it the other way too. So it doesn't really matter as long as it's drawn correctly. Question on those two reactions of carboxylic acids. Yeah, I mean, typically speaking, you typically will find it. I'll just draw this part of it. You typically will find those guys kind of near each other, just to indicate that, you know, that's probably the attraction that's going to happen. You know, if you're asking, could you just write like H2O plus Na plus the rest of it? Yeah. Yeah, it's fine. As long as there's a plus with this sodium, it should be fine. Other questions? Okay. All right. So carboxylic acid, salts, you do not need a name. But you do need to be able to obviously draw them from a reaction like that if it occurs. They are ionic compounds with strong attractive forces. They typically are room temperature. They have high melting points, and they're usually very soluble in water because, frankly, they're a salt. So they're an ionic compound. They're a strong electrolyte. They're just going to kind of break apart in water, which allows them to interact well. Because even though it looks really big and awkward, it is still ultimately like an ionic compound of a negative thing and a positive thing, which allows water to surround those ions when they're in it. and basically be dissolvent and be very soluble in water. Carboxylic acid salts, like I said before, are used in preservatives and flavor enhancers, and added to other things along the way. Why don't you write the reaction of propanoic acid with sodium hydroxide and see what you get. Okay, so let's take a look. We'll start with propanoic acid, which should be 3 carbons. Again, oic acid tells us it's a carboxylic acid. And again, we'll fill in our hydrogens here. We're going to react with sodium hydroxide. So this is your classic acid base reaction. H and OH going to come together there to make our water. And then really kind of put the other 2 parts together, and we'll basically get CH3, CH2, C double bond O. Once again, this is going to have a negative charge, and we will also have obviously our sodium floating around with it. Any questions on that one there? Carboxylic acids are part of metabolic process within cells. There's pyruvic acid, which you can see is our carboxylic acid group there. Lactic acid as well, also a carboxylic acid made through a reduction. And just like we talked about before, reduction here really of like a ketone, right? And we get our almost secondary alcohol part of it kind of be coming back in, just like we talked about there. And the citric acid cycle, or the Krebs cycle, we got a lot of these carboxylic acids. Again, this is a very common way that carboxylic acids are written in formulas. So if you see again that kind of COOH, that is definitely the carboxylic acid functional group. And that again is what it looks like when it is drawn out. So I would say that's a very, very common abbreviation. We see it with like acetic acid. It's very commonly written like this. And that means that we have more acetic acid, which is ethanoic acid. It is this guy is basically what it looks like. So that's a very common way that group is definitely written. All right, so we can move through oxidation and reduction going backwards. And the next thing we're going to talk about are esters, I think. And esters are basically like a carboxylic acid, except it's got a carbon attached. So no OH, the H is gone, and we have this as our functional group. So a lot of esters are responsible for a lot of things that we smell, and I think the lab maybe you do next week, you'll do that. You'll make a bunch of them and smell them. Don't smell them too deeply, but they will smell like different things. A lot of very aromatic type of guys are esters. So how do we make esters? Esters are essentially made through a reaction of a carboxylic acid and an alcohol. And it's in a reaction that is referred to as an esterification reaction. We take a carboxylic acid, which has this group, and we take an alcohol, which has this group on it. And frankly, we take out water. So we just like grab water out of it. Out goes water. And then essentially all we do is squeeze the 2 ends together that we took that's outside of the water part of it. So we basically just take this part, which is from the carboxylic acid. We take this part, which is from the alcohol, and we just squeeze them together, and we will get CH3, C double bond O, OCH3. And right there is our ester. In this case. And there is our functional group of our ester there. So this is what is referred to as an esterification reaction. You basically take a carboxylic acid, you take an alcohol, you take out water, and then just squish everybody together basically into one. And that's what we see here. You can kind of see our ester group that is formed there. This is what it looks like in line structure, carbon to oxygen to carbon, with our double bond happening right there. Yeah. So that is the reaction I was just talking about, our esterification reaction. It does involve H+. That is an acid catalyst. A catalyst, again, is just used to speed up the reaction. It'll have no effect on the actual outcome or what you're drawing. Also, a little bit of heat is used as well. And we get this esterification reaction. That means when we look at an ester, there's really two parts to an ester. So if we take this one here that was formed, and we take this ester, there's really, as I mentioned, kind of two parts to it. And where they come together is really right here between the carbon and oxygen single bond. And if you go away from the carbon oxygen double bond, so if you head away from the carbon oxygen double bond, that's going to take you to the alcohol part of your ester. And if you go through the carbon oxygen double bond, that is going to take you to your carboxylic acid part of your ester. And that's really important because that is how we name these guys. So the way that we go about naming these guys is the alcohol part is named as a group. So a one carbon group is a methyl. The carboxylic acid part is named on the number of carbons it has, which is 2, which is based off of ethane. And we actually will drop the E and put O8 at the end of it. So this is methyl ethanoate. And that comes from the carboxylic acid side. Some people will tell you just to drop the IC from the carboxylic acid name and put 8 at the end of it. You could do that too. Or you could go all the way back to the alkane and drop the E and put O8 at the end of it, however you want to remember it. So the way that we produce an ester, alcohol, and carboxylic acid together gets us our ester, and then we name it based on those two parts. Alcohol part first as a group, O8 at the end of the longest carbon chain from the carboxylic acid part. Any questions on that there? So let's just say I had this here. And I reacted it with why don't you draw what I would get, and why don't you also name it? Okay, so let's take a look. So we have our carboxylic acid, we have our alcohol. So when those guys come together, that's going to make our ester, and we're going to get that by removing water. So that's going to give us water. And what is left is basically we're just going to start to the left there and go to the right and put it together. And we will end up with I'm going to go across the box here to make my ester bond. And we will end up with this guy right there. Any questions on that? Now to name it, we always want to kind of look at it between the carbon and oxygen single bond. And remember, going away from our double bonded oxygen will give us the alcohol part, which is the first part of the name. That is 2 carbons, right? Which means that is a ethyl. Right. Now heading through the double bond going the other way gives us 1, 2, 3, and 4 carbons. So that is based off of butane, and that would then be butanoate, O8 at the end of it. So that little ethyl butanoate there, yeah. Any questions on that name there? So again, alcohol part first, carboxylic acid part second. If it helps like I did there, you could turn your alcohol around and kind of line up the hydrogen with it so you can kind of see where the water comes together and then just kind of squeeze everybody together to make the ester bond. Any questions on that there? All right, we will lay it up there.